Hi everyone, and welcome to lesson 3 on the electric field of a point charge. So here we're going to learn how to use something we call the field model to describe and to quantify the electric field strength that is produced by a point charge. Okay, so you recall that we learned about lots of models in Physics 151. So we'll continue to develop some models here as well. So we'll look at the field model. And so we learned about a point charge, right? Charged particles or charges, we can call them a point charge. And they will produce something we call an electric field, okay? So to first look at the electric field, I like to think about this this physicist Michael Faraday. So the development of electricity, the theories of electricity, of magnetism, these took place mostly during the 1800s. And Michael Faraday is one of the most important of the physicists when it comes to the study of electricity and magnetism. He was very interested in physics, but unfortunately, he didn't go through all like the elite training of, that was considered elite in 19th century England, and so he didn't really kind of fit in with those people at that time, the typical physicists at that time. So and he didn't do a lot of he didn't really know math either, which is kind of interesting because so many people associate physicists with knowing a lot of math, and so he really couldn't express the ideas he had mathematically, which I think was actually a good thing. It was really important. I think you'll see why in a minute here. But he wrote a letter to another physicist of the time, James Maxwell, who we'll learn about toward the end of our study of magnetism. And Faraday, Michael Faraday, he expressed a desire in this letter to make physics more understandable to people, to non-physicists, so that and not to rely so much on math. And so that's the quote I have here, is that when a mathematician engaged in investigating physical actions and results has arrived at his own conclusions, right? So somebody who kind of used math to discover some physical thing that was happening. So he says he does this and he comes to a conclusion, and then he says, may they not be expressed in common language as fully, clearly, and definitely as in mathematical formula, right? So he's saying, do we really need to show this in all the math? Can we do it without math? And he says, if so, would it not be a great boon to such as we to express them so, translating them out of their hieroglyphics, that we might almost work on them upon them by experiment. So you may have had if the experience that sometimes math and physics and chemistry and things like these are like hieroglyphics to you. Some people are like that, and that's fine. That's sort of how I was when I started out. I sort of identify with Michael Faraday because I didn't really care for math at the beginning when I was younger. But yeah, he's really saying here, do we really have to deal with this all with math? Do we really have to, predict things and find things out mathematically? Can we just, do experiments and try to, figure out what's going on and put it down in plain English, right? And so I would answer his question with a yes, a big yes, because too many people, and physicists included, they believe that physics can only be understood by having exceptional high math skills. Okay, but it's important to remember that math is just one of the ways we represent an idea. So recall from Physics 151, I went on and on about representations, about models, okay, and how equations were just a representation of some idea. Okay, I said, if you took it with me, I said you'll never hear me using the term formula. Okay, I hate that word because it implies some sort of magical kind of potion or something to me, you know, and that's not what an equation is. All right, it's just that, you know, it's the most, math is just the most concise way to represent an idea, and that's why physicists love to use it. Okay, that's the only reason. Okay, and we could also express an idea in words, graphically, in all kinds of ways. We don't have to do it mathematically. Okay, it's the most concise way. So I always like to try to have my students understand that physics is not about using equations and things. Okay, it's not. Equation is just a way to represent something. It's the quickest way to really come to understand something, to represent something, to come to a solution to something. And so a lot of people, don't like that. And so, that's fine. I didn't like it at the beginning either, but then I did sort of start liking math once I started to really get into it and to really understand it better. But anyway, Faraday, he had this lack of math skills. Okay, but it didn't stop him. It didn't stop him from becoming one of the most important figures in the history of physics. Faraday came up with this idea of a field that, which had a revolutionary effect on how we now understand electricity and magnetism. It's really not clear if Newton really considered it that much, this idea of a field or something similar. Because he lived during the time where remember, heretics were being executed for saying anything that opposed what was going on with the powers that be at the time. And so when Newton did consider any kind of interaction that didn't have some sort of touch, he described it as action at a distance. Okay, so this is like gravity. Okay, he explained gravity, but it wasn't like a contact force, right? The force due to gravity was not a contact force; it was a field force. Okay, so Newton didn't go into this this idea of what's going on, why are things happening when things are not touching. But even at Faraday's time, the physicists thought that, similar to Newton's idea of an action at a distance, that that some kind of forces were leaping across gaps. Okay, so they really didn't know this, and so Faraday comes along. He's got a very religious nature, as many did at the time, and he, due to his beliefs, he believed that space, right, empty space, was not really empty. Okay, he thought that divine presence had to be everywhere. So what we saw as empty was not really empty. Okay, something was there, and so this is how he developed this idea of a field, which turned out to be true. So interesting. That he used, sometimes we say you can't just use your belief to try to come up with something, but this is a case in point where it actually did work. So so we now know that there are electric fields, there are magnetic fields, there are gravitational fields, and other fields, and we can't see these directly. So although we can't see fields, just like we can't see the atom, we do see interactions that are produced by the fields. So for instance, we see evidence of a gravitational field when we drop something like our keys or our phone, right? We know something's there. We don't see it, but we see the interaction. We see something is causing something to do something that it ordinarily would not have done. So we can likewise see evidence of electric fields. So first thing I'll do for an electric field is I'm going to show you a little interaction that shows us the effects of an electric field. Okay, so what I have here in the middle is I have this piece of metal that is sort of like a point charge, and it's connected. There's a little wire connects it down, way down here off the screen, to where I'm gonna put some charge into it. Okay, so I have like a little charge generator, and I charge it up, and what essentially this is on top of it, I've placed this little closed piece of acrylic that has some oil in it, and all these green things that are in the oil, they're grass seeds. Okay, so grass seeds suspended in some sort of oil or something, when they're exposed to an electric field, they start moving around in the direction of the electric field. So it's an interesting thing, and a nice way that we can actually see that, yes, there are electric fields happening. So I hit play, and when I hit play, I'm gonna be charging, and you'll start seeing these grass seeds moving around in the direction of the electric field. And so you see them moving. It's a little tricky to see, to really see if you haven't really played around with this, but they're essentially going out in radial lines away from the point source. Okay, so it's hard to see, but you can at least you can see that something's happening, right? It's not just something's causing these things to move around, these grass seeds to move around. All right, so I said that they were moving around radially, okay? And so essentially this diagram, you can find something like this in your e-text. And so essentially you have a charge. So maybe in this image, there's a positive charge, or a point charge particle, whatever. So we'll call it a point charge. And it creates a field that looks like this, where there are these lines pointing radially outward. Okay, that's what a point charge, that's what the field, electric field of a point charge looks like. Okay, mathematically, a field is a function that assigns a vector to every point in space. Okay, so if I want to say, what does the vector look like? What does the field look like at this point? Well, it's a vector that points out like that. And if I said, well, what does it look like here? Well, it still points in the same direction, but it's going to be smaller. Okay, so it's going to be a bigger vector. The closer you are, bigger arrow, closer you are to the source, right? And it's going to get smaller as it goes further away. And so now we can develop a field model. Okay, we see that a source charge has to create the field. Unlike contact forces, though, where one of the interacting objects had to be the force agent and the other had to be acted upon, the source charge is not the agent. The electric field is the agent. The field is what's causing things to move around, okay? The charge itself produces the field, okay? But if we were to put something in the field, like a grass seed, right, the charge is not the agent that moves it around. It's the field that it's in the presence of moves it around, okay? So I'll get maybe taking a little getting used to. But okay, so we have an electric field, and it exerts a force on anything you put in the field, like the grass seeds that we saw. So so the electric field strength is equivalent to the force exerted by the field and the charge, okay? And it's related, and the units are newtons per coulomb, okay? And so we could also rewrite this in terms, of force, the force on Q. Okay, and when I say Q, what I mean is, all right, there's, let's say that there's a charge, capital Q. All right, let's say that is the point charge, the source charge, okay, it's creating the field. And if we put another charge, right, and we'll put this charge Q in the field, okay, we have to put something in the field, essentially, like a test charge, in order to determine what the strength is at a certain point, at a certain location in the field, okay, because it's going to vary, right? We could see just looking at the point charge, right? These lines that represent the field, they're very close together between here and here, here and here, here and here, here and here. But as we get further away, right, there's more distance, and so the field gets greater in between them. So it's weaker further from the source of that's creating the field. So so if we put so when we put a charge in the presence, it experiences a force, right, which is equivalent to the magnitude of the charge, right? This charge, okay, the charge that's in the field, not the source charge. It's equivalent to the charge times the electric field strength. Okay, so sort of like F equals ma, okay, because if you have, right, if something is exerting a force, right, the force depends on some aspect of the object, right? So with F equals ma, it depended on the mass. Right? If you had a larger mass, you could not exert the same amount of force, right? And cause it to accelerate at the same rate, right? If you had a smaller thing, it was easier. You had to apply less force. Okay, so a similar kind of thing, but except here with electric fields, we're talking about not the mass being accelerated. We're talking about the charge, the quantity of the charge. Okay, so a larger charge, there'll be a right. It has to. The electric field can't push it as strongly if it's heavier. You can think of it sort of like that. Okay, so if the charge that's creating the field is positive, and the charge that we place in the field is positive, then the force that the charge we put in there experiences is in the direction, is in which direction? So they're going to repel, right? If they're both positive, it's going to move that way. Okay. If the force is negative, it's going to be attracted toward it. Okay. And that's sort of how we define the direction of the field lines. Okay. Is that, if we put a positive charge in the field, which direction is it going to move? Okay. And we'll come back to this again when we look at what the field lines of a negative charge look like, which with the essentially positive source charges, point charges, whatever you want to call them, the field points away, okay, from the positive charge. And if it's a negative charge, the field will point toward it. So if we want to determine the electric field strength that's created by a charge at a certain, we have to, it's different, right? Depending where you are, okay? If you have a point charge, it's going to create radial lines around, and it's going to get weaker and weaker the further you go away from it. So it doesn't have a uniform field strength. The field strength, electric field strength, is not the same everywhere. All right. So if we want to know what it is, we have to put some sort of test charge in there, right? Because we know that if this is a positive test charge, it's going to have field lines that go like this, right, pointing radially outward. So there's no one electric field strength that it produces. Okay, we are going to see some special scenarios where there are constant, uniform electric fields. Okay, but not yet. We're just looking at right now. We're just starting out very simple with a point, just 1 point charge, one source charge. Okay, so if we want to determine the electric field strength, say here, wherever we want to determine it, we have to put a test charge there, right, to determine it. That's the only way we could find out what the electric field strength is at that certain location. Okay, so if we say that this is charge, we'll call it lowercase q, then what we need to do is if we wanted to say, let's say what we want to know, what's the electric field strength here, we need to put our test charge or our probe right there. Okay, so I'll put a little test charge there. Some color we can see. Okay, so there's our test charge. Let's call it Q1 or Q prime, right, whatever, we call it whatever we want. Okay, so we can find what the electric field strength is there. So we said the electric field strength is equal to the force on that Q prime divided by the charge of Q prime. Okay, the force, right? What do we know about the force? Force between charges is Coulomb's law. So that's K times the magnitude of Q times the magnitude of Q prime over R squared, right? Right, this distance squared. Okay, so that's the force, right? The electric field is force divided by Q prime. So we have the force here, and let's throw our Q prime in there. And right away, what do we notice? It doesn't matter what the test charge is. It cancels out. It shouldn't matter, right? So the electric field has a certain strength at this point. It doesn't matter what the charge is. Okay, the electric field still is going to have the same amount of strength. Okay? The only difference it will make, though, is if you put a larger charge there, then the electric field can only exert so much force. It'll exert a weaker force, okay, than it could on a smaller charge. There's a tiny charge, the electric field can exert a big force, right? Sort of like F equals ma, right? If you want to get something to move fast, right? If you exert certain force, you know, say to try to push a car with a certain amount of force, right? It's not really gonna move a lot, right? But if you exert the same amount of force to like a ping pong ball, it's gonna move really fast, okay? So it doesn't matter. the electric field doesn't really matter. It's sort of, this is what it is at this location, and depending on what you put there is what's going to happen to it. Okay, so this essentially comes out to electric field is K times the charge of the source charge over the distance squared. And if we want to put this in terms of epsilon naught, which we're going to want to do eventually, so I'm just going to start getting you used to looking at this. It's 1 over 4 pi epsilon naught times q over r squared. Okay, and so that's the how we can determine the electric field strength. And if it's a positive point charge, we know that the field points away. All right, so now here we have, this diagram is nice because it shows us how when you have a positive point charge or source charge, then the electric field points away. We can see the arrows pointing away. This is also a nice little diagram showing us, the vector nature of a field, right? So the point close to the field, it's a larger vector, right? Larger arrow, and as we get further away, we get smaller arrows, just indicating that as we get further away, the field gets weaker. Okay, and then now here we see with a negative charge, field points toward that charge. Okay, so maybe we could pause here and try to look at this diagram and answer this question. At which point is the electric field stronger? Okay. Well, hopefully you said it's stronger at A. Okay. Because it's closer. The closer you are to a point charge, that the electric field strength is stronger the closer you are. Okay, so let's do an example problem here, one similar to this in your homework, and so here we have an electric field, which we symbolize with E, and it's 100,000 newtons per coulomb. Okay, so we see the electric field here in the diagram. It's pointing to the right, and it causes a 5-gram point charge to hang at a 20-degree angle. Okay, so it looks like this point charge Q, so maybe suspended by a string, so maybe this could be sort of like a pith ball or something, and it's hanging at this 20-degree angle. So can we determine what is the charge on this ball? Okay, what is the charge on this ball? Well, we know its mass. We know the electric field strength. We're given an angle here. So what can we do here? Okay. Well, this is again another situation where you're going to have to pull out of your 151 toolbox. What's going on here? What kind of situation do we have? Okay, so we see here that the point charge is hanging at a 20-degree angle. Okay, it's not moving, it's hanging. So hopefully you recall the term static equilibrium. And in static equilibrium, what do we know about the net force? When an object is in static equilibrium, the net force is 0. All right, so let's create a little free body diagram here. We'll try to identify all the forces going on. Okay, so it's a little bigger here. So what do we have? Well, we have the bead here at the origin. Not the bead, the ball. Okay, And what forces are going on? What are all the forces happening here? Well, it's suspended, it's hanging, so gravity is going to have to be exerting a force here. Okay. Force to the gravity. The electric field is exerting a force, right, toward the right. So I'll do F, E, and there's something hanging it there, okay? So there's going to be some sort of tension, okay? We learned about tension in the previous course. Okay, so those are all the forces that are happening here, okay? And we're in equilibrium, so everything has to balance out, right? So gravity is pointing perfectly downward along the y-axis. The electric field strength is pointing perfectly horizontally along the x-axis. Okay, so the only thing that's not perfectly in one dimension is the tension. Okay, but what do we know about the tension here? Well, let's see. I'll draw a little dotted line here. This is 20 degrees. We know that, right? Okay. And the tension is going to have an x and a y component, right? So it's going to have, over here, we'll have Tx, the x component of the tension. And over here, we'll have Ty, the y component of the tension. Okay, so broken everything down into its components. So what do we know here? So what are we looking for, right? We're looking for what is the charge. We have a charge exposed to an electric field. And what do we know about that? We said that the electric field is the force divided by the charge, right? So if we rearrange it, if we want to know what the charge is, we can rearrange and say that it's force divided by electric field, the electric field strength. So we know the electric field strength, but we don't know what the force is. Okay, but when we made our free body diagram, we're essentially saying what's this force, right? Okay, so remember what we do with static equilibrium. We find the net force, the sum of the forces in the x direction, and the sum of the forces in the y direction. So first of all, we'll say the net force, all right, x direction. All right, so we have force Fe, force from the electric field, minus the x component of the tension. All right, those are the two forces horizontally. And since it's static equilibrium, the net force has to equal 0. So the statement tells us that the electric force is equivalent to the x component of the tension. Okay. And what do we know the Fe is, right? That's Q times E. Okay. And the tension is going to be T sine theta sine 20 degrees. Okay. So we have one expression now with Q in it. We know the electric field, but we don't know the tension. Okay. So maybe we can find the tension from the y component. Okay. So the net force vertically then is Ty minus force of gravity, equilibrium, so it has to sum up to 0. So the y component of the tension has to equal gravity. Okay, so the y component of the tension is T cosine 20 degrees. Force of gravity is mass times gravity. And now we have a second expression there. Okay. So we still don't know what t is, so we could substitute in is one way to do it. The other way we could do this is since we have sine and cosine, if we can divide the two expressions, right, by one another, what do we see is going to happen? So let's divide the first expression, the t sine 20 degrees equals q times e. Divide that by the other expression, t cosine 20 degrees equals mg. Okay, and what do we see happen? We see that, well, we don't need to know the tension. Okay, it's essentially doing the same thing as substituting, solving for t and putting it in the other one. But this is another way you could do it if you want. And then we know that sine 20 degrees over cosine 20 degrees is sine over cosine is tangent. And that equals to q times e over mg. Okay, so essentially then, room here, but move up here. So we want to know q, so solving for q, it's mass, gravity, tangent 20 degrees, all over the electric field. Okay, now we know all these quantities. We plug in and we get, I get 1.78 times 10 to the minus 7th coulombs. Okay, so you're seeing more and more how it's really important to have this prerequisite of mechanics before doing this course, right? Okay, so there's one last homework problem, very similar to the problem we just did. So that should help you out if you go over that part again. And there's a couple extra example problems that you can look at on the Moodle page under the chapter 22 extra example problems. Might help you out. But so now you should be able to finish whole of homework 1. And so finally, did you learn to use the field model to describe and quantify the electric field strength produced by a point charge? Okay. So we learned about this field model. Okay, a point charge or source charge. Oops. Point charge or source charge creates a field. Right, points radially outward in all directions. Gets weaker the further you get away from it. It's stronger closest to the source charge. We saw we need to, if we want to figure out what the electric field strength is, we need to put some sort of test charge or probe charge in there to determine that. Okay, and we also saw a couple ways that we can express how to find the electric field. Right, we use Coulomb's law, right, to look at that interaction between the source charge and the test charge, and that helps us to determine the electric field strength. Okay, so make sure you understand and really understand this. So far this electric field, what it is. I know there's only one question in the homework, but we're going to continue using this electric field strength and learning about it with multiple point charges and distributions of charges. So it's going to be really important you understand this field model. So that's it for lesson 3.